We present algorithms for moving particles to desired 2D positions when all particles get the same control input. Without boundaries, all particles would move identically since they get the same control input. We exploit interaction with a rectangular boundary to enable the same inputs to move particles independently. At left are two particles that start in the locations marked with squares and have goal locations marked with circles. The right plot shows a delta configuration space, which is the difference between the particles' relative positions. The reachable set from pushing a particle into a vertical wall is shown in green. The reachable set from pushing a robot into a horizontal wall is shown in blue. Delta G is the desired relative spacing. Delta R is a current relative spacing. When delta G is in the reachable set, 3 moves are sufficient to position the robots. When it is not, additional moves are needed, discovered using an A*-like algorithm. Using the configuration space, our algorithm finds the shortest path in 1 to 7 moves. The shortest path is shown as we move the starting and end positions. The commanded moves are shown at right. We require that the particles must start and end with at least epsilon difference from each other and the nearest boundary. Epsilon is a positive, user-defined value and is illustrated in gray. The longest path occurs when the particles begin in opposite corners and must switch places. This requires a total distance of 2 plus the square root of 2, or about 3.41. We extend the two-particle position algorithm to position n particles. The algorithm is an iterative procedure where the kth iteration moves the kth particle to the goal location without affecting the other particles. This is accomplished using drift moves that slide one particle along a boundary with no net movement of all other particles. At left is a simulation and at right a hardware demonstration using 1 centimeter magnetic particles driven by a global force underneath the platform.